We've now related angular displacement to linear displacement. We also spent time earlier in this course working on kinematics problems with linear displacement. Let's continue with the angular motion. What other quantities played a key role in linear motion? So think about that for a second before we pull the box down here. Okay, that's enough. Velocity and acceleration. And they were defined as velocity is the change in displacement per unit time, and acceleration is the change in velocity per time interval. Define angular velocity as the change in angular displacement, delta theta, over time. Also, define angular acceleration as the change in angular velocity, which we just defined up here, divided by time. Please note the Greek letter equivalents of v and alpha were taken for the angular equivalents of the linear motion variables. So for example, you have omega, which is the equivalent of v, and alpha, which is the equivalent of a. For a rotating rigid body, for every point on that body, theta is going to be the same, no matter where you are. Since omega and alpha are both defined according to theta, omega and alpha will also be the same for all points on a rotating rigid body. But the same is not true at all for linear velocity and acceleration. Let's relate the linear and angular velocity and acceleration to their angular equivalents. And here, just to remind you, here's omega and alpha. Omega is a change in angular displacement per time, and alpha is the change in angular velocity per time. We'll now do a little algebraic substitution. We're going to start with the definition for angular velocity, and that's right here. Omega is delta theta over delta t. And we're going to substitute in the linear displacement for the angular displacement. So let's recall S, linear displacement, is equal to the radius of our circular rigid body times theta. So theta will be S over R. We put that in over here. See how we substituted for theta. Now the radius is constant for this particular piece on the rigid body. So we're going to pull R out of the delta sign. So we'll have 1 over R, delta S over delta t. Delta S over delta t is just the definition for linear velocity, and we come up with this very key equation. Velocity of a point on a rigid body is equal to its distance from the center of the rigid body, its radius, times omega. You can feel this on a merry-go-round. The further away from the center you move, the faster you feel you're going. You're feeling the linear velocity. Your turn now. We'd like to derive the relationship between angular and linear acceleration. So start with the angular acceleration, substitute in the linear velocity for the angular velocity, and see what you get. So please take a couple seconds, pause the video, and then when you're done, come on back. Okay, you're back, or maybe you've never left. And here's how we do this one. We start with the definition for angular acceleration. It's the change in angular velocity over time. We substitute in omega is v over r. Once again, for a point on the surface, its distance from the center, or the radius, is always the same, so there's no change. So we'll pull the 1 over r out, and we get 1 over r delta v over delta t, which of course is the definition for linear acceleration, multiply through by r, and we get linear acceleration is equal to r times angular acceleration. When you work with rotations, this chart will become second nature to you. But for now, I strongly recommend you write it down. Make a chart in your notebook. Even though it's right here, you could take a picture of it, you could just print it out. There's something to be said for writing things out. It helps you remember them better. We start with the angular variables here, theta, omega for angular velocity, and alpha, and we define them in terms of their other variables here. We have linear, where you have displacement, velocity, and acceleration. And then we have here the relationships that we just derived algebraically. So please put this in your notebook and look at this and get very familiar. A nice way to remember it is the linear variable always comes first, then you have r, and then you have the angular variable. Signs are very important when you do dynamics and kinematics problems. You have to know if your displacement is to the left, if it's to the right, if it's positive or it's negative. We know how to do that for linear displacement, for example. If you move to the right or up, that's typically positive displacement. And of course, here's the caveat, that's arbitrary, but we typically do that method. Now, how do we assign a sign for angular displacement, velocity, or acceleration? Does right or up work with rotational motion? Does it work with a circle? Not really. It really doesn't work very well. So we have to come up with a different method of assigning signs. So let's draw a horizontal line here, like that. That's pretty horizontal. And you know from your math class that the horizontal axis through a circle is typically labeled as 0 degrees, and angles are measured in a counterclockwise direction. So for example, this angle theta would be measured like that. And what does that look like? That looks like 50 degrees. So we would call that a positive 50 degrees. If we rotate it down this way, and it looks like I made a slightly different angle, that we would call minus 45 degrees. So we're comfortable, or hopefully you are, if you go counterclockwise, it's positive. Okay? So once we get that, we can talk about the definition of angular velocity. Looks like displacement is going to be positive if we go in a counterclockwise direction. As this disk rotates, or somebody on the surface of the disk rotates in a counterclockwise fashion, so let's now put this point C here, this angle that it makes now is theta, let's call it C. This angle is bigger than this angle. So as we rotate in a counterclockwise direction, theta increases. Delta t is always dealt with positive, so delta theta over delta t must be positive. Since omega is delta theta over delta t, counterclockwise rotations, we will describe the angular velocity as positive.